say start recording. Nice. So hey, to everyone who's watching live or watching in the future, this is Andrew. I'm just going to show you how I would create a simple West Coast drive, single speed, 4-inch wheels, a similar version of what I would expect you to be able to do. If you were to recreate this and turn it into me, I would be content, even if you copied it exactly. That being said, some creativity would be appreciated, but it's whatever. So I'm going to start off by doing a layout sketch of my drivetrain. So before I even make any parts, usually I do a sketch of basically what it's going to look like, what the constraints are. My drivetrain, I'm going to limit myself to, let's say, so it has to fit in a 30 by 30 area, so 30 inch by 30 inch. So I usually start off by defining my area with a bounded box of construction geometry. So think of this like a top-down view, so to speak. And then I'm going to have my 2x1 rails, it's going to be 1 inch wide. I'm going to make this center point vertical. And this can actually touch the 30-inch edge. Doesn't need to do much from there. I'm actually going to say it's going to extend the entire width. So this is my piece of 2x1 tubing. It's my front one. And actually, I'm just going to real quick make my horizontal and vertical center lines so I can mirror across, just so I can be lazy. Nice. So I have my front rail, my back rail. Now I'm going to do my drive rails, and those are just going to, select other, select the, there. Select that piece in there, which is the width. So I can have my 2x1 be actually, 1 inch wide. I'm going to take that and mirror it across. Now how wide I want it to be and in what dimension really doesn't matter right now. For me, nominally, I'll do let's just say 2-inch wheel wells. I have 2 inches for my bearing block and for my wheels. We'll get into specifics about that later. I'm just gonna put that dimension up there. So let's look at what I have space-wise. So I'm planning to have my gearbox somewhere in the middle. I'm just going to simulate my gearbox space by this rectangle, pretending it's a top-down view. This is the approximate rectangle bounding my gearbox. I don't know what size it's going to be. I haven't made it yet. But I know I'm going to use 2 sims pretty close to each other. A sim is about 2.54 inches in diameter. So double that, so 5.08. So I'll round up to the nearest half inch. I'm just going to overestimate. I'm going to say it's going to be about 5.5 inches wide. Typically a good estimate for the drive. Let's see. It's going to be a single speed gearbox using a single stage. So I have 2 1/4-inch plates and then a gear stage that takes roughly about a 1/2 inch. So that's 1 inch, and then you'll say, sims are like 5.5 inches long. So I'm going to say this is like 6 inches long. Just a rough estimate. And of course, I don't expect y'all to be able to know these numbers off the top of your head. But in time, you'll figure them out. So I'm going to model my wheels. Now a wheel, if you look top down, is a rectangle with the length being the diameter. I'm going to say 4-inch diameter wheels. And my width really is going to be up to me. If you're going to be using some stock wheel parts like we have in our library, the Coulson wheels, you can check those measurements. Actually, yeah, I should probably do. I was originally not going to do that, but I figured since you're going to be doing that anyways, I was going to make my own wheels, but I'll just choose a stock. I'm going to do like a 4x1.5 Coulson. That exists, right? It's a 4x2. Is there not a 4x1.5? Yeah, it's 4x1.5. So I'm just going to quickly open this. Let's see. Oh, that's one of those bores. So round bore one, like this, and there's a hex bore. The round bore was what teams used before VexPro came out with the hex bore ones. At this point, there's no reason not to use the hex bore one. Oh dear. Is there no? Oh, here it is. Okay, here's the hex bore one. I didn't have it. And real quickly, because it's bothering me, I'm going to change that color to be something I can actually see. Nice. When I was younger, I made everything like dark black because that's how it looks in real life, and then I realized you can't actually see it in the CAD that way. So I settled with a little bit less color accuracy in CAD just so I can see it better. So this wheel, let's see, the approximate width. It says down here 1.689. So I'll run with that. And then it's going to be, same dimension as my gearbox, right down the center. Let's see. So it's not going to be directly on the tubing though, because I have that bearing block that we'll get into later. That goes to an 1/8 inch thick, and then I'm going to have a 1/16 inch spacer in there. So that's what 1/8 inch plus 1/16. So yeah, I have a nice little bit of wiggle room. What's this? A little less than like 0.25. Or is that quarter or 0.25? That's quarter. Yeah. Works for me. So I'll do that. And then I'll simulate my other two wheels. I can just use the equal relation because all my wheels are going to be the same size. And I'll say that's a vertical to that one. Now let's see. I want my wheel to be kind of far, but not too far. I also want it to be an approximate division, or an approximate multiple of 0.25, just because it makes certain things easier. So I'm going to say, let's see, this is currently, how far? 11.638. Can I do 11.75? Yeah. How much wiggle room does this give me? Quarter. Yeah. I want to be able to move it up and down by like, oh, well, no, okay, yeah. Actually, that works. Because the bearing block is going to have 3/8 inch of total movement, which means 3/16 in each direction. So 3/16 less than a quarter. This is nice. Okay. So I'll just put that there. And let's see, I'll just mirror that across so I can have my wheel side, and then I'll do the same thing. Oops. I don't want to get the tube. I'll just get the wheel separately, and then I'll get the gearbox. Just real simple. Did not get that wheel. Or that one. What's up with that? Alright, I think that looks good. Just mirror that over. Nice. So it's a pretty simple diagram of what my drivetrain is going to be like. And it's nice that we get all this done in the sketch, because we can always refer back to this for dimensions and such later. So I'm going to save this. Usually when I go to there. When I go to my project folders, I'll have, before I even have like, my different subassembly folders, I have a few underscores. Underscores, I just put underscores in front because it moves the folder to the top. And I'll do have like sketches or GXFs, different non-subassembly specific folders. So this is the drivetrain, this is the main sketch. I still use the naming convention most of the time. And I'll do, instead of a subassembly number, I'll put sketch and which sketch it is. Most of the time I just have a single sketch in its main. Sometimes I'll have a sketch for different subassemblies. If it's a larger robot. Either way, get that saved so we can always, refer to it later. We'll get started with making parts. Looks like this is made up of 4 pieces of tube, 2 pieces of 30-inch, and 2 pieces of 28-inch. Cool. So I'm going to start with the front and back ones because they're super simple. We'll extrude on the right plane. I use, by force of habit, use the right plane. You don't really have to, but I like doing so. For my front and back tubes, I'll use a 16th inch wall because they're not taking as much load from the drivetrain as the left and right rails are. I also use the term rail to refer to the tube. It's interchangeable. So now I extruded it. I extruded it mid-plane because I like doing that. Makes the symmetry really nice with all the planes. I can use the planes later. I do this cool little trick. I just skipped over it, and I should probably explain what I'm doing. When I do my hole pattern, I want it to be center down the length of the tube, but I also want it to start exactly a 1/2 inch away from the ends. Easy way to do that without dimensioning anything. I know my tube itself is 1 inch long, so half of that is actually 1/2 inch. So if I go to my 1/2 inch or my halfway point, it gives me that orange little line. So what this says is this line says it has to be center, and this line basically says the length is 1/2 inch. So I set the two equal. Easy way to get half corner right there. And I'll set that to 196, and I'll extrude cut. Oops, don't want to fill it. Going to the features, I go to a linear pattern, select any side length, as long as it gives me the direction I want. I can tell because the arrow's out there. And over here on the side where it says spacing and instances, I'm going to actually choose up to reference. What this will allow me to do is I will select the edge, my offset distance. I just click the up arrow to 0.1, doesn't matter what it is, but 0.1's good. And I'll say my distance between instances is 0.5. The nice thing is it just does it all for me. Now I can do, as an alternative, right, what I used to do, I used to use spacing and instances, and I would count each individual instance, right? The problem with that though is this one's 59, but for some reason if I wanted to change this length, right, if I want to make it 32, I'm now, I still only have 59 holes. Whereas, I'll change that back to 30. If I do up to reference, right, my reference point is the end of the tube, and I'm always, referencing off that position. I don't give it an exact number. I can go and say, 36, why not? And you'll see it'll just fill in the extra gap for the holes. So that's an easy thing to do. It's a nice little touch. So really for this part, for the front and back, this is it. That's all I really need for this rail. So I'm going to make a new folder, and it's going to be Andrew Personal Project 16 01. Let's call it the frame. I'll save this in here as Andrew PP 16 0101. So the first part in subassembly number 1. Cool. And then what was the size again? Go back to my layout sketch. My left and right drive rails are 28 inches. Good to know. So I'll start with doing the exact same thing for the most part. Use my center rectangle. I have a 2x1 rectangle. Use 0.125 as my offset. So what I'll suggest for all y'all is if you're for your front and back tubes, you can make them 16th wall, thinner, not always as strong, but it's definitely lighter. But for the inside, for you have your drive tubes and your gearbox and your bearing blocks, you're going to want to use 1/8 inch. And I'll extrude this to be 28. And I'll do the same thing with the holes. Extrude that out. Oh, yep, that's what I want. Linear pattern, using up to reference. Up arrow to 0.1. 0.5 spacing. Now, this is pretty much where we left off on the other tube. On this one, we're going to start adding some things in. Most notably our gearbox mount and our bearing blocks. So, should I do the gearbox first? No. I'll just do this. Yeah. So what I usually do is I already know what my gearbox is going to look like typically before I start the tube. In this situation, you probably don't know. So just follow along. If something makes sense, great. If it doesn't make sense, just trust me on it. It will later. Cool. So here's what we're doing. I'm going to simulate what my side rail is going to look like. Now I'm doing a 6-wheel drive drop center, which means if you look at my halfway point, the center wheel is going to be dropped by a little bit, actually that's the main point. The center wheel is going to be dropped a bit. The way I typically do it is I'll have the center wheel. Let's say if I want an 1/8 inch drop, I'll have the center wheel lowered by a 1/16 and the outer wheels raised by a 1/16. You can do it so the outer wheels are level and the center ones down by the whole drop. So that'd be like outer ones are at 0, centers at -1/8. It's up to you as long as you have that drop in there between the outer and inner wheels. For 6-wheel drive, typically 1/8 to 5/32 inch drops pretty nominal. Most of the time you'll get off fine with those, especially with Coulson wheels, which is what we're using. So I'm going to say these two are equal, and the distance between them is 1/8 of an inch. 0.125. Cool. Now, let's see. How far apart did I say my wheels were on the sketch? 11 3/4. So I'm just going to say distance between these 2 points is 11 3/4. So I have my position for my 2 wheels, or for my 3 wheels. I'm just going to model my wheels from the side profile. It's a circle, and it's a 4-inch wheel. That looks good. Do the same thing over there. I'm not going to deal with the other side because I'm just going to do this one and mirror it on over. The center is different from the sides, but the 2 sides are just mirrors of each other, so that's fine. Starting off with the wheel side, the gearbox side bearing block is a 1.5 inch hole with a mount that is 15/16 off its side. So it's 15/16 off center, or a total distance, if you do midpoint line like I just did, of 1.875. If you see, you want to measure that, it's 0.938 or it's 0.9375, just being rounded in SolidWorks, and that's fractionally 15/16. And that's going to have a number 10 through hole, which is 0.196. And then the other set of holes for the gearbox mounting is going to go here as well. And that's going to be 4.5 inches. Now, why 4.5 inches and why 1.875? It's because I told you to. For right now, it's all that really matters. Nice. Now for the wheel side, we need to put a bearing block in. And we're going to model that as a rectangle, which nominally is 1 3/8 tall and 1 7/8 long. But just for tolerancing purposes, I'm going to add 2 thou to each of those. So instead of being 1.875, it's going to be 1.877. Instead of 1.375, it's going to be 1.377. It's pretty fair. Now, a few ways to do the slots, because your bearing block slides in your slots. Typically, the way I've always done it is I do, a slot on both sides, because, that's technically what it is. Set them equal. Whoops. Use the equal slot. Make them 3/8 long. The radius is 0.196 over 2 because it's a radius. You're using number 10 bolts. And that's usually how I would do it. That being said, one of my students earlier introduced me to a much simpler method, which it's just as viable to use. I personally don't, just because I'm stuck in my ways this is a good one too. You just make one large one. It's all getting cut out anyways. Make the distance between the center of one end and the edge to be half of your travel distance. Instead of 3/8, you have 3/16. And do the same thing with the radius, 196/2. Works just as well. Now that's your bearing block hole, or the slot at least. However, you need your tensioning slot or your tensioning hole. You can have your cam tensioner in there. That's just a number 10 hole. Make it horizontal with the center of your bearing block. And you want to make a dimension between the center of the bearing block and the hole to be 1.875. It's a number that keeps coming up. It's a pretty good number. So I'm going to take that. I'm going to mirror all this across that little AB line right there. Get the same thing on either side. I'll go to cut extrude now. And I'm going to cut it all out. Through all, and that works nicely. I'm going to fillet these inside corners to about 1/4 inch. I'm going to use the fillet expert to select most of them all at the same time. However, where is it? Yeah, I usually will select all concave and just deselect the inside of the tube, because otherwise it selects these corners in there. I think I actually selected the tube wall. Yeah, let me deselect that. Oh, did I get it? And I got the tube wall again. It's pretty easy to weigh. If you see the cursor and you see that little rectangle next to it, it means you're selecting a face. And if I can get it right, oh, see the little line, it means you're selecting a line. There it goes. Oh, perfect. So now I should have only those selected. Perfect. And I just realized I did not select the right hole over here. So I'm just gonna go back to my cut extrude and select that. Yep, did not get that for the tension block. Cool. Yeah, so this is our standard drive rail. If you want to go a little lighter, you can pocket the inside area, this chunk of meat right here. Usually what I used to do. But that's not important. I'll save the part and get into an assembly. Now, let's see. Start off with a drive tube, just because that's how I want to orient it. However, when I first put a part in, it fixes the part and it creates it matches the part axes with the assembly axes. So, if I go to my part now, I can go to my front plane. It's the same front plane as the assembly. Top plane, same as top plane, yada yada. And I don't want that, because that makes my job, well, not harder, but I don't get to be lazy as much, and there's no fun in that. So I'm going to float the part, drag it out a little. My front plane is the one parallel with it, so I'm just going to mirror it across the front plane. I'll make another one. My top plane, I'm going to make that the bottom of it. And what I will actually do is I will use the right plane for the right plane, just so I can have it centered. Cool. So that looks good to me. And then I'll insert my sides, my front and back. I'm going to make this just by going the top's coincident with the top, the end's coincident with the ends, and then there's a 2-inch distance between that face and that face. And there's a 2-inch distance between these two faces. And if I do it right, I shouldn't be able to move anything because it is all fully defined. Fantastic. Sorry, long night. I'm going to mirror the front tube across the right plane. And that's the basic shape of my drivetrain. So I'm going to save the assembly. 01 frame. Of course, there's still a little bit of stuff to do, but I'll save that for a little bit later. For now, I'm going to start adding in my bearing blocks to my West Coast Drive section of the folder, or of the library. If you look at a bearing block, you have a thicker section and a thinner section. Thinner section goes on the outside, thicker section goes on the inside. It's kind of weird to figure out how to mate them. Good way I always done it. It's my favorite, using the width mate. If you go to the advanced mate section, use width. You can center something along two different faces. So I'll select the two side faces of the bearing block and the two side faces of the slot. And so I'm just going to center it in the slot. And I'm just going to put this face of the block coincident here. And I'll make them do the same width mate with the vertical, just because the top bottom width right there is 1.375, but my slot, I modeled it to 1.377. Perfect. So it gives a nice little wiggle room. Now if I were to measure the distance between these, it should be 1.313, some strange number. I can just get flathead bolts that are 1.375. If I go to my bolts in the library, number 10, flathead cap screw, somewhere around here is 1.375. There it is. Sometimes parts, when you introduce them to assembly, will show a sketch in them, which always annoys me. I just, disable sketches from the view tab. So I'll put these in, make them coincident and whatnot. It's just nice to model all your hardware in there. You don't need to do it, but it's good practice, especially when you start indexing assemblies and such. You have every part in there. So for this, I'm going to use Thunder Hex bearings, just because they're nice to use. No reason why not to. Oops. Bearing is all the way at the top, and Thunder Hex is always all the way at the bottom. Use flange bearings because those are the ones that sit nicely in this little area. So in this area, you have the round part of the bearing sits in it. Whoops, let me drag that out. This little recess right here, you put the flange coincident in there, and it sits nicely in there. Take out another one, make that concentric, and put it in. So that's pretty good. And since, I might as well, I'll just put my wheel and my spacer in there. I said I have a 16th inch spacer, 500 hex. 500 is 1/2, and 375 is 3/8. So I'll just make the round of this concentric with the round of that. Oh, we drag it out. And make those two faces coincident. Now if I go to my wheels, Coulson, 4.5, 4x1.5. Nice. So I'm gonna use this little round surface right there to mate to the round. I usually try to avoid mating the hexes directly because not all the hex models are the same. What I'll do instead is I'll make the round coincident with the round. I'll take a face of each hex and I'll make them parallel, so that if you look in here, oh, whoopsie-daisy. If you look at this face and that face and that face are now lined up. I don't think my color change worked either. It definitely looks like black here. Yeah, let's change that in there. Cool. And then I'll take this face, it's the inside face of the wheel, make it coincident with the spacer. Nice. And it looks like we have a good amount of room. Cool. So I'll save that up. And then, actually, no reason not to mirror the wheel across and the bearing setup. So I'm going to go back to my mirror. Actually, I should slow that down a little. Sorry. I'm going to go back to the first mirror component I made. I'm going to right click and edit the feature. I'm going to go select the wheel, the spacer, the bearing block, the 2 bolts and the other bearing. And that'll add them to the other side as well. And when I go to the second mirror component, I'm going to do the same thing, except this time I'm going to choose both sides. So I have my right side and my left side. The one I'm going to mirror to the side I mirrored. Usually it's a good idea to keep your mirroring constant, whatever side you're on. So, for example, this left side over here is mirrored, which means this is my constant. This is the side I should keep working on. I should add everything here. So when I eventually add a shaft and sprockets and such, I'll add them all to this one and then add the mirrors across. So far, so good. Now it's time to make my gearbox. So the first thing I'd want to do is open up JVN's Design Calc. I'm just going to bring that over here, and hopefully you can see it. If you can't, that'll be embarrassing, but we'll work through it. I'll just verbally explain everything, because I'm apparently good at that. I'm not. I'm really not. Anyways, I'll go to my custom 1-speed drive tab, because it's a single speed. Change my motor to a sim motor, gearboxes and drivetrain 2, because we have one on either side. Motors per gearbox are going to put down to 2. Total robot weight is 154 pounds. Well, you get that right. This is a theoretical max of 120 pound robot, plus 20 pounds of bumpers, which is 140, and 20 pounds is usually the max bumper weight. And then you have our 14 pound battery. And batteries and bumpers aren't included in the 120 pounds. So that's approximately a 154 pound robot. I'm going to say all the weights on the driven wheels. Don't worry about speed loss, constant, and drivetrain efficiency. You'll know when to mess with those. Later point. Wheel diameter, this is a 4-inch wheel. Alright. Now I'm going to shoot for something that's approximately, but since single speed, I'll shoot for like 15 feet a second. It's not bad. So my driving gear is going to be the pinion on my sim motor, sorry. That's going to be either 11, 12, 13, or 14. My driven gear is what's going to be on my wheel end. 54 is too small. 11 to 60. So let's see. 4-inch diameter wheel. Real quickly. I think I can fit a 64 tooth, no problem. 15.99, that's close enough. Yeah, it's 16 feet per second, that's fine. 11 to 64, yeah, that'll work. The outer diameter, what I'm looking about whether it'll work or not is, will the tooth, or will the gear fit? Because it's on the same shaft as the wheel, right? So you want your gear that's on the same shaft as the wheel to be smaller than the wheel. If it's too big, your wheel's not touching the ground, the gear is. The outer diameter of a gear is determined by the number of teeth plus 2 divided by the diametrical pitch. In this case, it was just 20 because we're using 20 DP gears. So it would be 66 over 20, about 3.3. 4-inch diameter wheel, that's fine. Could probably go to 66. Yeah, I'll go to 66, 11 to 66. Good 6-to-1 ratio. That works. Yeah. So let's model that. Make a new sketch. I'm going to model it by making 4 as my 4-inch wheel and make that construction geometry because my wheel isn't going to play a part in my gearbox. And then let's see, this is going to be my 66 tooth gear. So I'm going to model the outer diameter of the gear. There's a few ways you can model gears. You can do the outer diameters, the inner diameters, the pitch diameters. The easiest way is you just use the pitch diameters and make the pitch diameters tangent. It requires no math or no equations in SolidWorks. You just make the 2 pitch diameters and call it a day. I don't like doing that because it doesn't show you the full size of the gear. I like seeing if my gears are going to collide with anything or if they'll take up the same space. So I think the extra math is a little worth it. So this is a 66 tooth gear, so my outer diameter is the tooth count plus 2 divided by diametrical pitch, which is 20. So that'll work out nicely. I'm going to make that construction geometry as well. I'll make a line going up. I'll put, or actually not even going up, no, I'm sorry. This is a single stage. So what I'm going to end up doing is I'm just going to put my motors off to the side. Now a sim is 2.54 inches in diameter. Coincidentally, it's a pretty good number. I'll make a real quick center line. I'm just going to do one side and mirror it over. Now I have an 11 tooth pinion on the sim, but to note, with the 11, 12, 13, and 14 teeth gears, the 11 and 13 teeth gears are addendum and dedendum not modified. Don't need to worry about the fancy terminology. All that means is the 11 tooth gear is the same size as the 12 tooth gear, and treat it as a 12 tooth gear when you're doing your sizing math. The 13 tooth gear is the same size as the 14 tooth gear. It's treated as a 14 tooth gear. So even though we're using an 11 tooth pinion, I'm going to say my outer diameter is equal to 12 plus 2 divided by 20, so it'd be 0.7. And the distance between the centers, so even though I used a midpoint line, the distance between my centers is going to be equal to the sum of my two teeth. So this is going to be, even though it is an 11 tooth gear, I'm going to say a 12 plus, I think I use 66, divided by twice the pitch diameter, so divided by 2 times 20, or just divided by 40, and then I'm going to add 2 thousandths between the distance just to make sure, so I can count for machining tolerances, make sure the gears aren't too close together. That's why I added the double parenthesis there in the beginning. In the previous one, I just did a single one. So I do double parenthesis open, then I close one, close the other, and then add 0.002. So good enough, that is where my motor is going to be. And the sim has a boss extrusion in the front. It's 3/4 of an inch, so I use 0.755 for clearance. Use a midpoint line for the bolts and such. Actually, I don't want that to be vertical, so I'm going to use one of these holes, or one of the mounting holes, to not only mount the sim, but to mount the gearbox. So I'll make that a little diagonal in a moment. Make these 0.196, because that's the through hole for the number 10. This would be 2 inches long. And if I were to look right, actually I'll draw the rectangle. So this is going along my drive tube, right? Or, whoops, yeah. Sorry. It's going along my drive tube. I'm not going to model the full 30 inches, but I'll say, what is this, 12, say 8 by 2, yeah. So this is my drive tube, and this is all centered. Oh. But it's a 1/16 of an inch below center, so 0.065. So this is what it's going to look like relative to the tube. I want to use one of these holes to mount the gearbox. Oh, not what I wanted. So I'm just gonna real quickly, yeah, that works. Actually, I'm gonna change up my mind like a bunch of times while I'm doing this. I had a plan, and then I realized I'm gonna scrap the plan, and now I'm looking back at it. I think I'm going to go back with the original plan. So I apologize for the inconvenience, but I promise you're going to learn more because of this, for sure. I'm going to move my motor up there. I set these two lines equal because that's the distance between my two motors. So I've been working with 3-inch wheels for the past few days, so I forgot I could literally just put my motors up here. Whoopsie daisy. I didn't like that. Cool. I'm just going to delete that and then mirror it across, because I forgot mirroring's a thing. Oh, not offset. Remember, kids, don't CAD while tired. Nice. So this is my two sim motors. I'm gonna put very little room between them. I'm gonna put like 20 thousandths. So it's like 0.020. All right, cool. Yeah, if you got to go, I'll post the rest of the recording later. So I'm going to put my the line for my sim motors and make that perpendicular, just so it makes sure it's equidistant. And then my bearing is 1 1/8 inch outer diameter, so 1.125. See what time is it? Oh, okay, I've been doing this for a while. Time flies when you're doing CAD. I wish. So I'm gonna have my bearing block holes, which are, you know, the 1.875. And I'll have my other mounting holes, which are the 4.5. Actually, hold up, sorry. The bearing, or these holes are going to be 1.5, because we're going to thread them 1032. So we'll do that. This is going to be 196, and I'll mirror that over. Now we're going to put an outer hole here. So this is actually not a hole, it's just extra material, and we'll call it 1 inch. So we're going to have a big pocketed boss, and you'll see how that works out in just a bit. So it looks like with this, all being said and done, we have the main part of our gearbox. What we're going to end up doing is we're going to connect the outer layers. So we're going to connect the outside to the sim, you know, connect the two sims across. Could totally be mirroring this, but nah, a little bit of overlap there. Interesting. Now for the bottom, I could just be like, oh, you know, have some clearance there, call it a day. What I want to do is I want to make it so that I don't want my gear to touch the ground if I can avoid it. Sometimes I don't do this, but if you ideally could just create a little bit of an arc beneath there and have like a 1/16 of an inch between the outside of your tooth and your plate, just to make sure if there is any skidding, it's this plate that's skidding and not the teeth. Like, you don't want to be loading your gear teeth like that. So I'm going to take this and I'll attach them to both ends and I'll make them tangent. Cool. So now I have the basic outline of my drivetrain gearbox. So easiest thing to do from here is I can go extrude the plate. Gotta make sure I get that little area in there. Nice. These plates are typically 1/4 inch thick. So that looks good. This is the plate. What I'm going to do, first thing, I'm going to go to my features. I'm going to use my hole wizard to tap these two holes. So the reason I made them 0.15 is because the threaded hole for number 10 is 159. But if I were to dimension it as 159 in the sketch, it would say, oh, you can't cut through here because you don't have a little bit of material to cut through. So technically the hole's already there. So it wouldn't let you do it. So I just go to 0.15 and then use the thread, the hole wizard to make it turn to go into 159. Now on the outsides with these two holes, remember those 1 inchers we put? We do that because there's a counter bore for some really large, well, not really large, 3/4 inch tubes. It helps just make the gearbox a lot stiffer in West Coast Drive gearboxes. So they're about 3/4 inch diameter, 0.75. So for a clearance hole, just add some little room in there. We'll make them 755, add 5 thou. And we're going to extrude boss space sorry, not extrude boss, cut extrude, not all the way through, just halfway, so we'll cut an 1/8 inch in, and that'll be pretty good. That's our gearbox plate. We can pocket it, but we can do that later. So I'll make a new subassembly for my drivetrain. I'm going to say gearbox. It's going to be 0201. Nice. So we'll make a new assembly with 0201. I'll draw out another one, and I'm not sure if I mentioned this earlier, but you probably see me when I was doing assemblies. I would just drag out another part. The way I do that is if you hold Control and you click on a part, you can pull out another one. Makes it super convenient. So I turn this around so that the inside counterbores are facing each other. I'm just going to make these concentric, so the two plates are equal, just at some mysterious distance apart. Right. Cool. And what I'm going to do is, on the rear, I'm going to put my bearings and my motors in. I'm going to use a hex or a thunder hex shaft to go all the way out. Because I'm going to have my bearing block out here, and that bearing block's going to have a thunder hex bearing in it. But at the very end, really don't need anything special, so to speak. So I'm just going to do a 1/2 inch round bearing, so 500 flanged. I'll make that concentric. I'm going to put the flange on the outside because there's no point in putting it on the inside. I would put a flange on the inside if I could geometrically retain it, and what that means is if I have, a flange on the inside of this plate and a flange on the inside of this plate, you have a shaft in between, and something pushing against the flanges to prevent the bearing from popping out, you can geometrically retain it, which is really ideal if you can. A bunch of other gearboxes will do that, but we can't do it on this one, so there's no point. And let me just check my gears. Actually, while I have the bearing tab open, I'm just going to drag out my thunder hex bearing. I'm just going to leave it there. Okay, so you see it disappeared. Sometimes SolidWorks does this thing where it if you see it, it's in my feature tab, it's just not where I put it. It'll automate something. So it tried to automate it to the other bearing. It's like, oh, you have a round thing that looks exactly like the other round thing, so clearly you must want it right next to the other round thing. And it's no SolidWorks, it's not what I want. But can't be mad at SolidWorks for too long. You can, but it's not healthy. It's just a CAD program. It's dumb. I'm going to go to my gears tab and go to my 20 DP gears. I'm going to hex 500, just 1/2 inch hex bore gears. Let's see, do I have a 66 tooth gear? I do not. Oh, today's your lucky day. So VexPro now carries every tooth size from 14 to 84. That's even. So 14, 16, 18, 20, 22, 24, all the way up to 84. So that's why I use 66, because it's just 2 above 64. I don't have the gear, but this is the perfect opportunity to teach you how to correctly download gears and fill the library with parts. So if the library doesn't have a part, we need to add it. So I'm going to open up my web browser, which again, I'm hoping you can see. I don't actually know if you can. Usually I'll go to West Coast Products, but I don't know if they have all the gear CADs there yet. Under motion, go to gears. I'll go to 1/2 inch hex bore gears. CAD file. I need to find 66 tooth. 66, cool. Oh, there's VersaKeys in it. Does it matter? Doesn't matter to me. Is there no regular 66 tooth? Wait, if it's VersaKey, do I actually have it? I may actually have this downloaded. That would be in VK hex. VK stands for VersaKey. I do have it. How interesting. Alright, well, it's not your lucky day, I guess. I won't teach you. Actually, I will. Because I just did it. So you download the zip file, drag it to a desktop, go back to SolidWorks and go to your desktop, Open up the part. There's a few things you're going to notice. Number one, the color's off. Most importantly, the color's off, which sucks. We auto-assign the material as 6061. It's not actually 6061, it's 7075, but it really doesn't matter for this case. We don't need to change it. What we'll end up doing is we'd save it under a file name that matches everything else. However, the most important thing, I go to a pre-existing gear, copy appearance, go to the new one, paste appearance over the entire part, because appearance is important. I'm not going to save this because I actually have the part right here. Anywho, let's make that there, concentric over here, and then coincident at this face. And really, that's it. So I'm just gonna put my bearing block in. It's a single reduction gearbox. That's all I really need. You can experiment with, instead of doing 11 to 66, you can do like 12 to 44, and then 14 to 34. Up to you. You can make a 2-stage if you want. It's definitely not bad practice. For now, I'm just gonna do single stage because why do more than you need to do, right? And we get my WCD bearing block for the gearbox side. I'm gonna mate this by these two holes, the ones that are exactly 1 and 0.875 apart. And then this is the interesting part. I distance this front face to this back face by using a distance mate of 1 inch, because that's the inch that my tube is. The reason I don't just make things coincident is because of this little, if I go to the side, this little bit right here. See, I don't want to make this face coincident with that face. And the reason is it's purposefully made a little short, so when you screw it in right, it squeezes the tube a little. Just to make sure you grab hold of it tight. And distance between that face and this face, 1.375. So I'm going to put in my bolts. Number 10, flathead cap screw. 1.375. Turn off sketches because they annoy me. And let's put that in. And then flathead is just coincident with the surface. And that looks good to me. And I'm just going to, when I eventually mirror things over, I'll just mirror that over. So I'll take my bearing and I'll put that in here. Put the flange in there as well. And then, let me see, what's the distance from here to here? 1.063. Works for me. So I'm going to get a normal, actually, yeah, I'll make a custom spacer. What I was going to do is I was going to go over, Vex Pro sells these spacers. I can go over here and go 500X, and they're in like 16th, 8th, quarter, half, 1 inch and 2 inch lengths. What I was going to do is going to go to put a 1 inch in there and then a 16th inch in there and call it a day. But since we're doing Thunder Hex, I figured we might as well show you how to make a Thunder Hex spacer, because you can use regular hex spacers for that, but if you want to do a custom spacer, it's actually really easy for Thunder Hex. 299 part, shooter box base. So Thunder Hex spacer is going to be 3/4 inch outer diameter. It's going to be 14 millimeter inner diameter, just round, because Thunder Hex outer, if you can remember, it's hex but with rounded corners, and it's 13.75 millimeters. What we found was, if you just get a chunk of 3/4 inch diameter Delrin and you chuck it in a lathe and you use a 14 millimeter drill bit and you just drill right through it, then you're pretty much good. It acts as a good spacer and it sits on the shaft pretty nicely. So when we do that, I'll change the material to ABS just because it's close enough to Delrin. And I'm sure there's a Delrin material in there, but it's not on my favorites, so I'm too lazy to add it in. And from there, I could be good to go, but no, the white's not right. Let's remember that. It's rules to live by. So we'll go to appearance, and we'll change this to the second darkest black, just so it works. And because that actually will be the color of the Delrin we're using, so it works out nicely. go back to my GrabCAD, user projects, test West drive, gearbox. Instead of retyping in the name, I just click on the latest file, go in there and change the 1 to a 2. Super easy. I'll set this concentric with that. Whoops. Let's see, I want this face to be right on the bearing inside race. Cool. So that looks pretty even there. And I'll make that coincident with that. And that's a really tiny gearbox, but it works. So I'll get my spacers in, my big one, 0.748 inches. So I'm going to extrude that. It's just 0.75 inch diameter tube, 16th inch wall. I believe I said 748. So I'll save that as another part. Now, in actuality, this is not the best practice. I totally don't need my second plate. Like, these two plates close together serve no purpose. I could have one plate and bolt it directly to the tube, because that's because it's a single stage, right? If I'm doing it this way so I can teach you good practice with multiple stages, and when we eventually do shifting, it'll look like this as well. So I'm going to take that surface, make it coincident, take that one, make it concentric, boom. I know I have clearance because my sketch showed it, because I used the outer diameter. Then I'm going to put a nut on this end. I should have nut there. It's going to be a 1032 lock nut. It's going to go on that face to that face. Oh. Well, let's see. My bolt's going to go from a little further than here, so I'm actually going to be coincident with the face, and I'll show why in a moment, to, let's say, here, 1.223. So if I were to add an 1/8 inch, that's approximately 1 3/8. So I'll go to bolts. I could use a button head, but I'll just use socket heads, cap screw. I need a 1.375. Do I not have that? I have 1.25 and 1.5. That's weird. Probably exists, I just don't have it. I got a button head because I know it exists there. It does not. Does it really not? No way. Alright, we can go on an adventure to McMaster. There's no way this bolt doesn't exist. Thread size 1032. Length 1 1/4. Yeah, 1 3/8. What the hell? Alloy socket. Oops. Yeah, why do I not have that? So I was good lesson for you all around, I guess. Valuable information. Download the CAD. Change the material to steel. I'm going to delete the threads because I don't need them. They make my life annoying. So I just delete the hex spiral. And I'll leave the second little sketch right there. I can delete the sketch too. Go to the equations because I broke some equations because I deleted things that the equations were a part of. It's alright. Let's just click on it, click delete, call it a day. Go file, save as, 299 library, bolt, number 10, socket head cap screw. I'm just going to delete all this last part except for the part number, which is the 90901, whatever. And I'll put the naming convention in front, SHCS, socket head cap screw, underscore 10-32, underscore 1, underscore 375, which is 1 3/8, underscore, and then part number. Perfect. Older version file, save as. Nice. So if I go to library now, I don't know if it'll have actually updated. I may just need to pull the part out manually. Oh, there it is. Nice. So that'll be concentric in there. I'm going to move distance mate between here and here and make it 1/8 of an inch. And the reason is because that's going to be my tube wall thickness. But that looks good to me. Okay. I'll add my motors in now. Or where are they? Motors. I have sim motor. I'm just going to make this coincident to this hole. And that hole coincident to that, or concentric, sorry, to that hole. Make these two faces coincident. Nice. And then I'll just go back to my gears. 20T, sim pinions, 11 tooth. I want to use the default configuration. Make that concentric with the shaft. And that's pretty much exactly where I want it. Can I go here? That's going into the motor itself. Can I go here? It's going outside the plate. That's annoying. So yeah, I'll advanced plates width. I'll put it literally in the middle of the two plates. Because, why not? It's good enough. If I were to go to a section view, oh shoot, I can't do that. It's actually inside the sim itself. So this little area right here is the sim. It's going inside. So I can't do that. That's annoying. I'll just delete the width mate. Alright, what I'll do is just make it some distance from there. I'll make it like a 16th. Alright, at least it doesn't exit the plates, which is what I'm trying to avoid, so that's fine. And now I'll finally go to my front plane, and I'll mirror it across. Select the motor, select the pinion, select the bolt, select the tube, select this, select that bolt. I think that's everything. Nice. Yeah, it's good. I could put in the bolts for the motors. Not a bad idea. Actually, a pretty great idea. Usually want to go into the motors by like 1/4 inch. So these are being 1/4 inch plates. 1/4 and 1/4 is half. Put that in there. Put the face up there. Oh, I'm going to do the face first on this one because it's so far back. I'll go back to my mirror and I'll add those in. Nice. So really, on my front plate, if I wanted to get fancy, I could like cut out most of this because these holes don't do anything, those holes don't do anything. Yeah, I could cut out almost all of that, but I'm not gonna. Actually, what I should do is put a space. Yeah, I'm gonna do that. Whoopsie daisy. Teaching you good practice, so you're welcome. Find the distance between here and here is 0.498. Put a spacer in there, 196 inner diameter, and 0.3125 outer diameter. Typically I do 0.375 because this is so small, I can get away with this. Midplane, 0.498. Grab CAD, Andrew, test WCD, gearbox, blah, blah, blah. Go back to assembly 2. Where did that go? It's here. Just double, triple check. Yeah, that clears the sim by a lot. This is approximately 1, so I want 1 1/4. Button head cap screw, and I know that one exists. There. So this will go into the sim, but it'll also work as a spacer for the gearbox, adding some rigidity in there. Don't need it, but when you get to the bigger ones, it'll count. So I'll save this up. 1602 gearbox. So I got my frame. I'm actually going to have to open a new assembly now. I'll put the frame in there. And I'll put my gearbox in there. I'm not done with my gearbox yet, but I'm just going to start placing it. So I'm going to put this hole there. Whoops, back up there, bud. And this one through here. So I'll make this face coincident there. You'll see, oh, you won't see it, but yeah, so the bolts go inside there, and they're actually completely perfect. They're coincident with the face. And you're probably wondering, how do you get the bolts in there? Because the bolt head is bigger than the bolt itself, and you have that same hole on either side. What I haven't actually done yet, and probably won't do, sometimes I don't model it, I just do it in real life, is you drill out this face to be a little bit bigger. You use a 3/8" drill bit. You'll machine out the hole to be 1/96, and once you make it, you put the tube together, you just drill it out by hand. You can model it, and usually I do, but it is 11:51 at night, and I've had a long day, so I'm not gonna. So let's see, I'm going to go back up to my assembly, find my front plane, or whatever main plane I want to mirror across. I'll put my gearbox mirrored as well. Nice. So that looks good. I'm going to close all this stuff because I don't need it. I actually haven't looked in a while. I wonder if anyone's actually watching. I mean, this is more importantly, it'll be recorded and everyone can see it later. Is anyone actually watching? I have 5 viewers. What the heck? Do you not have anything better to do? Oh, I mean, you're watching me, so no, you don't. Anywho, so I guess I do have viewers. Hi viewers. I usually make these videos not live. I'll record them, so I'm not used to talking to an audience when I'm doing my SolidWorks stuff. So just like my other wheels, I'm gonna add a spacer. The reason I put the spacer in is just because those Coulsons sometimes they don't like butting up against the bearing too much. Go back to my wheels put my wheel into his. Wheel's part of the assembly too. Oops, select the hex. If you notice I haven't made any shafts yet, I usually save the shafts for last. But speaking of last, it is about time to do that. So I know how far my hex shaft has to go now, right? So I have to go from this face to the front of that bearing, or rather to right here. According to SolidWorks, that's 3.601 inches. I'm just going to do the real simple way of making shaft. I know there's technically more efficient ways, but I don't care. Make 0.5. This is slender hex, so 13.75 millimeters. And it has a 201 hole in the middle. So I'll take that profile and extrude it. So this was 3.601, but because for tolerancing and stuff, and because I have to fit a snap ring at the end, I'm going to add 10 thousandths to every end that I have a snap ring on. So because this is only a single end, I'll add 10 thousandths. If I had a snap ring on either end, I would add 20 thousandths. So plus 0.01. And now I'll add my snap ring groove. Convert entities for that hole because I want to keep the hole there. It's for a 1/2 inch snap ring groove. It's 0.468. It's going to be 40 thousandths thickness. And the reason I know this number is because I've been to the McMaster site so many times. If you go to the McMaster site and you check on the snap rings, they'll tell you what groove thickness it's supposed to be. So this is 468 diameter, 040 thickness. And usually on the end I'll put 060. Just keep it a clean number. And then that's good for now. On this end, this goes into that 1/2 inch round bearing. So I'm going to turn that down to 1/2 inch, and that bearing itself is 0.3125 inches. And because I have a snap ring on the other end, oh wait, I'm gonna sneeze. Sorry about that. 3.25, and I'm gonna add 10 thousandths. And I'll do the same thing, 0.468, 40, oh whoopsie daisy. If you're seeing, I'm getting a lot of features here. There are methods of doing this where you can do it in a single, get most of it done in a single revolve. And sometimes I'll do that, sometimes I won't. It's really not that important, especially for such a simple shaft like this. For more complex shafts, I'll definitely do it. I'll chamfer both edges because it looks nicer and because it makes it easier to get the snap ring on. And this is my drive shaft. Oh, not in there. Gearbox. Nice. So I'm going to position this by putting it against the bearing because that is where technically my tolerancing is. And because it's Thunder Hex, it's mostly round. If I just find a round surface to mate it to that's in line, so like that gear nub right there, that works. And then for my sanity, I'm just going to make these parallel. And there you go. I recently added snap rings to my library, so y'all should be using these as well. When you bring in a snap ring, it will give you some number and some number underscore GRV. GRV just stands for groove. Use the groove one. See if it opens it up a little, so it simulates being on a groove, which is coincidentally the only place we'd use snap rings. Like we wouldn't have a snap ring and just not have it on a groove. So that works nicely. And I'll put one on the other end as well. Nice. See, I think for the most part, the gearbox is done. No other shafts to make, no other spacers. I could pocket it, but I'm not going to do that in this video. We're running long enough as it is. So that's good. We'll call that a day. No, wait. I'm dumb. I apologize for all these mistakes. Normally I don't do this, but like I said, it's been a long day. I forgot. Also, I spelled something Adnru. Oh wow, I am so out of it right now. That's fine. Let me explain what I did wrong. You're going to have sprockets on either side of these. I didn't put the sprockets in. It's a really simple fix, don't get me wrong, but just goes to show how important sleep is, kids. And I know if you're one of my students, you don't get enough of it. So what I'll do, I put the sprockets in here, 25 sprockets, hub, 18 tooth. Pull another one out there. Make it concentric. Put this face up to that face. Oops, make the two faces parallel, if it'll let me. Alright, let's make it concentric with the shaft. Just because, even though it does not matter, because you will not see it at all, for my peace of mind. There. And we're going to put this end, right up against the gear. And that front front face there is going to be 3/16 away from the front there, 0.1875. So all we're going to do with this, we can go to our custom spacer. I'm going to add 0.1875. Save that. I gotta remeasure all these now. How far away is this? That is 0.91. So I'll take that number, add 0.91. And the distance from here to here is 1.408. 1.408. I have to use different bolts here now because these aren't going to work. I have to use different one here too. Well, this is why we do the math, I suppose. See, that's 2.133, so I can use 2 3/16 or 2 1/4. Bolt. Number 10, socket head cap screw. 2 1/4. Distance 0.125. That's good. And what's that to that is 1.908. So if I add 1/4. So actually I can just use 1 1/4 for that, or 2 1/4 again. Sorry. Yeah, that's good. So I'll go back to my mirror and add those in. Alright, that looks cleaner. For some reason it was looking suspiciously small earlier. I just didn't think of it. Much nicer. Cool. We'll save that up. Alright, now we'll get to the fun stuff. Implying, it wasn't all fun to begin with. Get the sprockets in, make a belly pan, and then my favorite part, we call it a night. So we'll pull a sprocket over here, make it concentric with the bearing block, get the interface and make that coincident with the interface of the aligning sprocket. We'll do the same thing, pull it over here, but we're going to flip the sprocket around just so we can save some space. And then make that face coincident with this face. Nice. And again, just for me. But for the CAD, it doesn't matter at all. And like when you're doing CAD, it shouldn't matter. The only reason I put that in is because when I do renders, I want it to look nice. So I'm going to go back to my frame now and put my tensioner cams in. So we go to my WCD folder, take out WCP cam. So the way this works, you spin it and it contacts this and it pushes it aside. I'm just going to get a little close and that'll work. And I believe it uses 1 1/4 or 1 3 or 1 1/2. That's wrong. Go to button head bolt 1032 1 1/2. I need to tomorrow get that 1 3/8. Alright, that looks good. Important thing to note. Oh, I put it in the wrong one. Should have put it in that one. I got lazy. That's whatever. Sometimes when you mirror stuff, it doesn't always work out right. So you go to go to the arrow screen to look at the different views of it. Let's see. I want WCD cam. Click this little arrow. You can choose the different views. Unfortunately, it's not being nice to me with this one. So, where'd it go? Did it even mirror it? No? Okay, that's weird. Drag out a new one. I'll mirror the bolt because the bolt works nicely. Sometimes it just does not want to deal with the cam, getting it in the right position. See if it'll do these ones. I bet it'll do one of them right, and the other one it'll just complain about. Yeah, it's not liking that one. This one, nope, not liking it either. But can I fix them? Let's find out. Let's see, WCD cam. Nope, nope, nope. Not gonna like that one. What about the other one, WCD cam? You gonna play fair for me on this one? Nope, the hole's in the wrong spot. Nope. Alright, it doesn't want to play nice. I do these by hand. I hate doing these by hand, but whatever. Whoops. Rotate it till it's approximately over there. Alright, that looks good. So we got the cams in. Go back over here. Let's see. I'm going to leave out a little bit of detail work just because it's literally past midnight and I started this at like 10:45. So I've been doing this for a little over an hour and a half. So detail work I'm going to leave out. I'm not going to put spacers right here, even though you should. I'm not going to put the drive shaft in. Those shafts. But I mean, I'm pretty sure students will be aware you need to put a shaft in between your wheels. You need to put a spacer in there, have a snap ring on either ends. And then last but not least, the belly pan. And this is probably a part, if anyone should pay attention to, you should pay attention to. And figure out what the dimensions between I know it should be 30 over here by 26 over here. Yeah. So I know the distance between the outer of these two walls and the outer of those two walls. So it's going to be 30 by 26. Put this on the top plane. Start with a rectangle. I'm going to make it my outer size, 30 by 26. I'm just going to right away extrude that by 1/8 of an inch. My belly pan is going to be 1/8 of an inch thick. I'm going to do that cornering technique. So I want it to be a 1/2 inch off either end, but I have nothing to compare it to, so I do have to dimension one of them at least 1/2 inch. And then 0.196 for my hole. And normally I try to avoid sketch patterns. SolidWorks doesn't like them too much, but I haven't found a better way to do this. So I just literally dimension it out. I could probably do, no, wait, nope, that wouldn't work. Yeah, so this is probably the best way to do it. Dimension it out, and then it's blue because it's undefined. What you gotta do is tell it that yes, SolidWorks, I want this to stay horizontal, and I want the distance between that to be 1/2 inch, and it's pretty good. Make a line right there because I'll mirror across it. I'll do a linear sketch pattern again, this time with the first hole and the other hole. I'll turn my quantity on the X down to 0 or down to 1. I'll put it up on Y, flip it around, make it 0.5, all that pretty stuff. And I'll keep increasing the instance count. And I'll do the same thing. Tell SolidWorks, yes, I want them vertical, and yes, I want them 1/2 inch apart, even though I already told you that. I didn't click dimension X or Y spacing, which is why I have to do that. Go to mirror, and I'll select everything except for the middle ones. You can still select the middle ones, but it's redundant, so it doesn't matter. Mirrored across, and then cut through all the way up. Now I get to chunk out the inside. We're going to offset the entire thing by 3/4, not 1 inch, even though it's a 1-inch tube. We're actually going to cut in a 1/4 inch onto either side of the tube because that's extra material we don't need. We're going to make a diagonal line, and we're going to connect the vertical and horizontal lines to the diagonal. Let's see, this is 24.5, this is 28.5. So I'm going to take this and make my X the 24.5 and divide it by the number of diamond patterns I want. 7's usually a good number for this size. If your belly band gets bigger, you might want to try 8. And put another diagonal here. And here's what I'm going to do. I'll click O, go to offset. I want to have a 3/16 inch total strand width, so I'll go 3/32 to 0.09375. Select both of those and bidirectionally offset them. And I will extrude cut. And I cut out these 4 little triangles. And I'll use the magic of linear patterns to do the rest for me. So first I'll click on my X. It'll say up to reference, but I want spacing and instances now. My distance is going to be equal to that 24.5 divided by 7. Oh, whoops-a-daisy. Divided by 7. You can see it's spaced out evenly, and my instance count is going to be 7. Likewise, direction 2, do the same thing. I had the 28.5. I'll divide that by 7. It's be some weird number, but I don't care. And I'll make my instance count 7. So when I click enter, it gives me this nice little diamond pattern. Before I finish that up, though, I'm going to put my gearbox plates in, or not the plates, but the you make a slot for the gearbox, rather, so that you can take it out if you need to. So with my gearbox is in this location, it's horizontal to the origin. If I go back to my assembly, let's see. How wide is this? At its widest point, I'll go from there to there. Measure, and I don't want center, I want maximum distance, and this is, you're joking, 5.5. Okay. I'm pretty sure that's what I have in my sketch too. That is hilarious. I did not do that on purpose, folks, I swear. I'll make my area a little bigger though, just so I can give myself some leeway. I'm going to say 6 inch. And what's my distance? From there to there is 6.385. I'm curious what I put in my sketch. Just 6, okay. I underestimated this. I forgot I had to put sprockets in. 6.385, so I'm going to call that 6.5. Or 6.5, I have to add 1 inch because I'm counting for the tube. 7.5, it's not bad. So I'm going to offset these now to the outside by 3/16 of an inch. And actually, to make my life easier, I'm just going to delete this dimension. I'm going to say it's going to line up right where this cusp is. Because what's going to happen is I'm going to add material in here. And when I try and fill it, I'm going to fill it here and fill it there. And that's going to be too close to each other. I'm just going to move that out a little bit. It'll make my life much easier. So I'm going to be adding material in here. I don't want it to extend over into this area. So I'm just going to go a line down to there. And a line down to there. I'm going to select the area and extrude up to surface, up to the other surface, or you can just go blind by 1/8, but up to surface in case I need to change my thickness later. Go back into here and create a rectangle, and I'm going to make it collinear with all the sides. So what that's going to do is it's going to select the entire area without having to redo any of the math or dimensions. Oops, there it is. Linear to there, so we'll cut that out. Whoops-a-daisy. I didn't mean to do that. Or I did, but rather what I ended up doing was this right here. I did not want to do that. I try and avoid having half holes. Easy way to avoid that is, I could just fill it in if I wanted to. But there's an easier way to avoid that, and that's just by making it so this line doesn't intersect anything. So I'll just add another 1/2 inch to that. Yep, and that fixes the problem altogether. Next thing, let's see, I will mirror across the right plane. Whoops, not shell, mirror. I'm going to do my boss extrude and my cut extrude. That gets both right there. Now I'm going to cut out the outside bit because I don't need all that material on the outside. Remember how I said, even though my tube's 1 inch diameter or 1 inch wide, I was only going to go 3/4 offset. Well, now I'm going to go 1/4 inch offset from there, because that's just weight I don't need, right? Oh, so my SolidWorks does this weird thing sometimes where if you offset entities, it'll like deselect the center position of previous sketches. So what it's doing is it thinks this center is no longer there, or if it's not there, it doesn't think that this is contacting there. So I'll just reselect that, and that's fine. So I'm going to cut all this excess material out because that is just waste that I don't want and I don't need. Oh wait, now that is a problem. I do not want that. What I'll have to do is I have to offset the line itself. Let's select chain. When I offset the plate, it tried to go off on the inside here too, which is not what I want. There it goes. We'll remove all that. Fill it the outside. All the outside corners should be about 1/4. I'll use connected to start loop. The inside, normally I would hold off on filleting the inside until I put all my electronics on, but this is just practice for all y'all. So this is going to be an 1/8 inch fillet on the inside. Usually I can just do the second one from the inside to connect it to internal start loops, 411 edges. Sounds about right. Give it a second. Imagine having to select all these by hand. I used to do that before I knew Fillet Expert existed. Alright, and that's my belly pan. I don't want to save it in Gearbox. I want it to go in frame. Alright, actually, not my assemblies. Go back to the frame subassembly. I want to put as much in the subassemblies as possible. I don't want to put much in my main assembly. The main assembly should just be subassemblies. So now with my belly pan, let's see. I save that as adnru as well. That's gonna bug me. It's whatever. I have the plates, the planes that I purposely put in the center so I can align the planes without aligning to a specific hole. It makes my life easier. And I'll just make the top plane of that coincident with the bottom plane of that. You can see how it lines up nice and perfect. And it has those slots for my gearboxes too. Okay, I'll save my frame. I can actually probably close out of that now. Close out of my sketch. And here it is, in general, my West Coast Drive. Let me see. Chain's gonna go from there to there, from there to there. There's a way I would model chain, but it's 12:20 in the morning, which I know isn't too late, but I've been doing this since technically yesterday, so I don't want to make this go any longer than I have to. So yeah, this is it. I'm going to save this as Andrew PP 16 test WCD. I'll upload it to GrabCAD so y'all can see it, and I'll try getting this video uploaded overnight. Okay. Hopefully this has been helpful. I can see my last viewer just left. So long. Thanks for the ride. Anyways, yep, students, hopefully if you can find yourself watching this, make my life easier. It'll make your lives easier. If you lasted this long, all 1 hour, 43 minutes so far, congratulations. If not, I totally understand. All right, I'll catch y'all later. Bye.